All right, everyone. So this video is going to focus on titrations, and that's what this next section is all about. So if you've taken 114 or 115, there is a chance that you have exposed yourself to titrations already in our program. So just a very quick review of titration. This is going to require a very long burette, typically around 50 milliliters or so, and this burette is filled with a titrant. All right, so burette has titrant on the inside. The titrant is typically a solution. Ding, 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 ding. This is a standard in solution course. So a solution with a known concentration. And that typically means that you have made this solution, or that means that you've ordered this solution, and this solution has been standardized. And standardized just basically means we know the exact concentration if we've made it. Very often when we make something in a laboratory environment, that concentration is not identical, or that is not expected to what it should be. It's always probably a little bit lower or a little bit higher, and standardization will allow me to go through and figure out what this known concentration is. So down below, we typically have some type of sample, and that sample is something that we need to know more about. So this sample is typically, we want to know what that concentration is. This is an unknown to us, and we use our titrant in order to figure out what that known concentration is going to be in the sample. So the reason that I'm bringing this up, we're just going to talk about it in a separate kind of area of standards and solutions course, because a titration is a very common method. And that common method basically means I'm probably going to see it very often in a laboratory environment. And sometimes they give me the calculations of what I need to do and what numbers go where, and sometimes they don't. But titrations are not meant to be very difficult. So the issue that I need you to understand here is that there is a solution with a known concentration up in the burette, and we want to know most of the time the concentration of a sample based on that amount that I'm getting ready to add in. All right, so what this means to us as far as the math goes is that if the titrant is giving to me, and I know the concentration because it's been standardized already, then that titrant will have typically a molarity. Now, it might not be a molarity, it might be a percentage, it might be a part per million, it might be a part per billion. It could just be anything that it wants to be, but very often, especially in the beginning, we need to talk about or look at molarity in terms of concentration. Again, doesn't have to be. Everything works the same that I'm getting ready to show you, no matter what concentration that it's going to be. And then finally, with the titrant, we're often going to get some type of color change or stopping point. And that color change probably means that I'm going to be adding milliliters of titrant into the titration for that color change to happen. Now, I want you to sit back and take a look at what we've got. We have molarity and we have milliliters. So what this means is that if the concentration is given to me in molarity, molarity equals moles over liter. I mean, that has never changed. That's something that has went back weeks and weeks ago when we first learned about molarity. And it's all coming back. So this molarity number, I know because it's printed on the bottle or it's been standardized. I know what that is. The number of liters here, that number of liters is in reference to the number of milliliters that it took for the titration. I just need to basically take the milliliter, divide by 1,000, and that will give me liter. All right. So there we go. That's a quick fix for that one. And then this way, I'll take my molarity and I'll multiply it by the liter, and that will give me the number of moles of titrant that the titration took in order to give me that color change. That's always typically the very first step of a titration problem, right? The titration problem is going to say, You put this into the burette, and this is your titrant, and this is the known concentration of that titrant, and it took 4.5 milliliters to titrate. Okay, well, take the basics that we've learned from weeks ago, take the molarity that the problem gives you or that you are using in the lab, multiply by the milliliter, but convert that into liter because that's the molarity problem. It's got to be moles per liter. That is the definition of molarity. And then calculate for the number of moles of titrant. That is step number one. This means that at this point now, you know the amount that was needed in order for the titration to take place. All right, so that's typically always the very first step. Now, any curveballs that can happen here? And the answer is yes, there are curveballs that can happen. And the issue is molarity. Very often it is molarity, but there could be maybe concentration units that you're not accustomed to. So part per million, that's also a concentration, but of course you would not use the molarity formula to solve for these. Part per million is milligram per liter, so it would tell you the number of milligrams that maybe that solution took in order to titrate. Part per billion would be the same thing. You would not use molarity. Normalities, very common for acids and bases. So if you're given a normality problem, I would probably recommend to you take the normality values that are given, convert those to molarity first, and then use the molarity formula from that point on. So it's just an extra step that you're going to have to take care of. And then finally, sometimes the concentration could be given to you in milligram per milliliter. And those are great because I don't really need a molarity formula at all, right? These units are in milligram per milliliter of titrant. So if it took 5.4 milliliters, then if you know the concentration in milligram per mil, well, you take the milligram per mil and you multiply by something like 5.4, which is how many mils it took to get the color change with, and this will give you the number of milligrams that are present as far as the titrant is concerned or the sample is concerned. So it really just depends on the concentration unit. I want you to kind of take a step back in some of these problems. Look at the concentration unit. Molarity is going to be common. Molarity is what you'll see all the time. Molarity, if it's not present, will probably be something like normality, just to add that extra step in to get you to realize how is normality connected to normality. And then, if it's not one of those two, it could be any of these other concentrations. Just take a look and imagine what those concentration units are supposed to represent. All right, so that's step number one, finding the amount of titrant. All right, so step number two, very often the next step of these titration problems is taking the amount of titrant that we have from our burette, and we have to relate that in some form or fashion to the amount of sample that we have in the flask that sits below the burette. All right. Before you can do this, you have to know a balanced chemical equation. A balanced chemical equation, folks. We've talked about that a few weeks ago, right? In some of these other lecture modules. We need to be able to look at equations. We need to be able to balance them. We need to be able to figure out how does one substance kind of relate to another substance. So in this example, A plus B goes to C and D. That's a general template for a chemical reaction. Very often, I'm going to have to go through these. Sometimes they're going to be balanced for me. I do not have to balance chemical equations every single time. If I see numbers that are here in front of these compounds, then that probably is an idea that this thing has already been pre-balanced, and I will be able to pick out the mole ratios from this point. However, if it's not, then you know how to balance chemical reactions now. We go through, we take a look at the individual components, we add the coefficients, we make sure that the left-hand side is balanced with the right-hand side. So in a reaction, I hope that it's balanced. If not, we need to take the extra step and do it. Go back and watch those videos if you need help. But in a reaction, very often, One of these, doesn't really matter which one, is going to be the titrant that I'm using in the burette, and the other one is probably going to be the sample that I am titrating with, or that I'm titrating for. All right, it's always going to be one or the other. And I'm going to look at the coefficients that are in front of these components, and those coefficients will give me a mole ratio. So again, go back, take a look at some of the stoichiometry. It's all been leading up to this, really, right? It's all of these different individual topics that are kind of morphed together now into something that we call a titration problem. So for instance, if this is hydrochloric acid and this is sodium hydroxide, these two things are going to react together in a titration. I'm going to add until I get to a color change, and then I'm going to stop. So in a balanced chemical reaction, I might see a 1-to-1 in front in this reaction as it takes place. And if so, that's great, because the amount of titrant in terms of moles, if I was working with molarity, would equal to the amount of sample that's in the flask. Again, and that's also done in terms of moles. So if it's 1-to-1, that's great. Take the molarity of the titrant, multiply by the liter that it took to the titration to take place. That will give you moles of titrant. Moles of titrant equals moles of sample. They are 1-to-1. If they're not 1-to-1, folks, go back, take a look at the mole ratio numbers. You're going to be able to use those mole ratio numbers in order to figure this out. So let's just pretend, right? We're just pretending here. What if this was a 2-to-1? Okay, well, the titrant is going to be the one that I'm going to start out with first, and the amount of titrant, and let's say that our titrant is NaOH. The amount of titrant that it took was 0.0030 moles of NaOH. All right. And the question is, how many moles of HCl? Something completely different in the sample, right? That's what this is all about. It's completely different. I need a mole ratio in order to figure this out. So I will divide by 1, set up my dimensional analysis problem. This is the titrant. This is what was in my burette. Moles of NaOH on top, moles of NaOH on bottom, and I need to go to moles of an acid. So let's just say that this is not HCl here. Let's say that this is probably a different type of acid, H2SO4 maybe, who knows? Okay, so if I'm titrating sulfuric acid and I'm using sodium hydroxide in order to do this, then I can set it this mole ratio, but I need the reaction first, right? Okay, so NaOH and H2SO4 is going to undergo a double replacement reaction, a neutralization reaction, and the Na and the H switch places, and that will give me H2O, which is going to be water, and Na and SO4. But it's actually Na2SO4 because the sulfate is a -2 and the sodium is a +1. So in order for this to work and balance out the proper way, I need 2 sodiums for the sulfate. So now I need to go through and I need to look at my balanced chemical equation because I don't have one. I need to do that myself. So there's 2 sodiums over on the right hand side, and now there's 2 sodiums on the left hand side. All right, there's 2 hydrogens here, plus 1 more, that's 3, plus another one because there's a 2 in front, so that's going to be a total of 4 hydrogens, right? So I've got 2 hydrogens here, I need to put a 2 there to give me a total of 4, and then I look at my sulfate group. My sulfate group, I can look at this all together because it stays together. SO4 on the left, and there's SO4 over on the right-hand side. So at this moment, everything is balanced. My coefficients are present. I'm good to go. But if I need to finish this titration calculation, 0.0030 moles of NaOH is what the titration required. And based on this balanced chemical equation, because it's not 1-to-1, here's my moles of NaOH. Just like before, NaOH is there. There's a 2 in front. So I'll put a 2 there. And then H2SO4 is up here on top. H2SO4 is there. There's not a number, so it's understood to be a 1. So a 1 goes on top there. So I'll take my 0.0030 and I'll divide by 2, and I'll get an answer. And I'll get 0.0015 moles of H2SO4 that is in the sample, the flask that sits below. Now, we're still not yet finished with a titration problem. So finally, our last step is, what does the question ask for, right? We did step number 1, which was to figure out the amount of titrant that's needed. And then step number 2 is to relate that with something that we're after in our sample, because that will typically require some type of balanced chemical equation. And now step number 3, in the previous example, we had 0.0015 moles of H2SO4. So the question could be, how many moles of sample do you have of this component? So if so, then this is perfectly fine. This is our stopping point. We do not need to go any further. The question could say, well, how many grams of H2SO4 do you have in your sample? Well, how can you relate to mole to gram? Go back, watch those videos. I mean, that's one of the reasons that we did all of those, right? So we can use here formula weight, because formula weight is the number of grams per mole of sample in order to calculate that type of problem or that type of answer. All right, and then the question could say, well, what is the concentration of the H2SO4 or whatever kind of component that I have in the actual problem? And if it's concentration, you just got to kind of keep in mind, what does concentration actually mean? So concentration could be in terms of molarity. So they want you to take the moles of substance that you have found, and they want you to divide by the liter of sample that you used. Now, keep in mind, this is liter of the sample. So if you add water, that water does not get added into the mix. That is not what this is all about. It's the concentration of the sample, not the concentration of the sample plus the water that you used, just to beef up the volume to see the indicator a little bit better. So that is one option that they could ask. The other option is normality. So they could say, well, what is the normality of the sample? If so, then my advice to you is get to molarity first. And then when you get to molarity, you can then relate it back to normality in that way. Another one, they might ask for parts per million. What's the concentration in parts per million? Well, you know that that's milligram per liter. So if it is milligram per liter, folks, you've got the sample size. The sample size you actually added to the flask yourself before you titrated it. So you just need to convert that over to a liter. And then in order to get milligram, well, look at what we did up here at the very top. This question said, well, what is the gram? So if we can get gram using formula weight, then we can get milligram by taking another step forward. We can just multiply by 1,000 in order to get milligram. So we'll take the number of milligrams and we'll divide by the total liter of the sample that you used in the very beginning. ppb would be the same way. ppb, though, I want you to kind of pay attention to. It is not milligram per liter, it's microgram per liter most of the time. All right, so any of these concentrations are fair game. It does not have to be molarity in titrations every single time. It doesn't have to be normality every single time. They can ask for these concentrations any way that they see fit. So again, it's all about realizing what those units are supposed to represent. All right, so if I had to do a summary of a titration problem, the first step is to determine the number of moles, and that's kind of important, the number of moles of titrant almost every single time. Number 2, we need to use an equation. And that equation will tell us a mole ratio. And that mole ratio will allow us to solve for the number of moles of the sample that we are after. And number 3, then we're going to have to report concentration. So that will often mean take the number of moles in step number 2 and do something with it. Divide by a liter to get molarity, then multiply by a factor to get normality, or take the number of moles and multiply by formula weight to get the grams of substance that's present in the sample, or if it asks for other concentration units, do the math as appropriate. And that kind of math I'm not going to go over because I've already done that in previous modules, in previous assignments, and you've done question after question after question on all of those conversions and how they work. All right. So that is the idea with a titration. You got to know something about your sample, you got to know what you're looking for, and you have to know the chemistry that goes on between the titrant in the burette as well as the sample in your flask. So these 3 steps, pretty standard, and in the next video we'll go through maybe 1 or 2 examples of titration problems just so that you can see how these are going to work together.